All right, let's do this. We are about to crack one of the trickiest topics in coordination chemistry, the one that can seriously make or break your rank in CUET. No fluff, no wasted time, just the stuff you absolutely need to know. Let's get into it. What if the number one reason students lose marks on ligands questions has nothing to do with memorizing crazy names or charges? What if it's a simple, sneaky conceptual trap that examiners just love to set? Well, once you see it, you'll never fall for it again. It all boils down to this one simple idea: confusing a ligand that has two potential hands with a ligand that actually uses both of those hands at the exact same time. And hey, you're going to want to stick around, because at the end, I'm going to reveal a super ligand that kind of plays by its own rules, and you absolutely have to know it for QET. Okay, real quick, let's make sure we're on the same page. A ligand is basically just a grabber. It's a Lewis base, which is a fancy way of saying it has extra electrons it wants to give away. It uses these electrons to grab onto a central metal atom, which is a Lewis acid. It wants to take those electrons. Simple as that. Giver and a taker. Okay, forget all the complex textbook jargon. From this point forward, we are just going to count the hands. Denticity is just a word for how many hands, or donor atoms, a ligand uses to grab the metal at the exact same time. This is the whole game. Seriously, pause for a second and lock this idea in your head. Got it? It's all about how many hands it's using right now.
So first up, we've got the simplest ones, monodentate ligands. These are your one-handed grabbers. Think of something like ammonia, NH3, or a chloride ion, Cl-. They just latch on at one single point. And because it's only a one-handed grip, the complexes they form are, well, they're not super stable.
Now we're leveling up to bidentate ligands, the two-handed grabbers. And here's that key word again, simultaneously. A ligand like ethylene diamine, which we just call ene, uses both of its nitrogen hands to grab the metal at the exact same instant. And when it does that, it forms a ring. This ring is a total game changer for stability. And of course, if you can have one or two hands, why not more, right? That's where polydentate ligands come in. These are the multi-handed grabbers. They use more than two hands all at once to build this incredibly stable cage-like structure around the metal. They don't just grab it, they basically trap it. All right, so that's the foundation. Pretty straightforward, right? Good. Now let's shift gears. The next part is where the confusion really kicks in for most students. This is the trap that separates a decent score from a top-tier one. So you're going to want to pay close attention. Let's talk about the ambidentate trap. I like to call this the imposter ligand, because it looks and feels like it should be a two-handed grabber, but it's not. It's a trickster, and I'm telling you, CUET examiners love testing you on this. So here's the difference side by side. A bidentate ligand uses two hands at once. Period. It forms that stable ring, and it bumps up the coordination number by 2. Simple. Now the ambidentate imposter, it has two possible hands, but it only ever uses one at a time. It might use the nitrogen or it might use the oxygen, but never both. And because of that, it never, ever, ever forms a ring. This is the core mistake. Okay, your turn. Time for a quick challenge. Pause and think. I've got two options for you. A, ethylene diamine, and B, thiocyanate. Which one is the imposter? Which one is the ambidentate ligand? Don't just keep watching, actually pick one. Lock in your answer. And the answer is B, thiocyanate, SCN-. Why? Because it can either grab with the sulfur or with the nitrogen, but never both at the same time. Ethylene diamine always uses both of its nitrogen hands together. See the difference? If you got that right, awesome. You just dodged a major trap. Okay, so I keep going on and on about these rings, right? Bidentate and polydentate ligands form these rings. But so what? Why should you care? Why does making a little ring give these ligands some kind of special power? Let's stop looking at the what and start asking why. This brings us to what I call the chelation superpower. Chelation is just the fancy name for this ring-forming ability of our multi-handed friends. And in the world of coordination chemistry, that ring structure gives the molecule one huge advantage: massive stability. So, to be super clear, a chelating ligand is simply any bidentate or polydentate ligand that successfully grabs the metal ion and forms a ring. The name actually comes from the Greek word for claw, which is just perfect, isn't it? It literally grabs the metal ion like a crab's claw, locking it in place. And the result is what you see here. It's called the chelate effect. A complex made with a chelating ligand is just way, way more stable than a similar one made with one-handed ligands. Think about it. That ring structure physically locks everything together, making it so much harder to break apart.
Now, this entire idea, multiple hands leading to stronger grips, which leads to more stability, it brings us full circle. It's time to go back to that super ligand I mentioned at the very beginning, the one that every single CUET student has got to know inside and out. Let's unlock the final boss of ligands, the ultimate chelating agent, EDTA. More specifically, its ion form, EDTA 4-. This thing is pretty much a guaranteed source of questions.
So what makes EDTA so special? Well, for starters, it's hexadentate. That's not 1, not 2, it's 6 hands, 6. And it uses all of them at the same time to completely wrap around a metal ion, forming this unbelievably stable cage. But even that isn't its most important feature. The part that always gets tested is its one unbreakable rule.
And that rule is this magic ratio, 1-to-1. Always. Because EDTA forms such a perfect cage, it always binds to a metal ion in a 1-to-1 ratio. It doesn't matter if the metal is calcium 2+ or iron 3+, one EDTA molecule grabs one metal ion, period. Remember that number, 1-to-1.
Okay, let's lock this in with a rapid-fire recap. This is your mental checklist. Monodentate, one hand, weak grip. Bidentate or polydentate, 2 or more hands, makes a super stable ring. That's chelation. Ambidentate, that's the trap, the imposter. It has 2 hands but only uses 1, no ring. And finally, EDTA, the king, 6 hands and that magic 1-to-1 ratio. Got it? So the next time you face a coordination compound question, don't just try to memorize. Just ask yourself, how many hands is it using right now? Is it making a ring? Or is this that ambidentate imposter trying to trick me? If this hands model clicked for you, hit that like button. Now go crack those MCQs.